Okay, so now we are starting our lecture, and today we will consider the second method, that is dealing more with the discrete function, not with continuous function like traditional Fourier series or Fourier transform. And I'm starting sharing my screen. And we will see what we have at the presentation. Okay, so our main topic today is discrete Fourier transform, or shortly DFT, like an acronym. We will use it also, so you should understand this. And direct, yeah. Some question?
Yes, teacher. Sorry.
Yes.
Before to starting the class. First question: can you also send us by Google Class the recording of the class?
Yeah, of course. I just answered to Ahmed. He asked the same. I will upload this recording to the Google Classroom, so you will be able to
yes,
take it.
Sorry, because I don't know why my internet connection is really poor in this moment, so I can hear you, but
yeah,
with
okay.
some lag.
Could you hear me
as,
now normally or not?
Yes. Sometimes is the connection. I can hear you clearly, but now it's normally. And
Okay.
another thing, already Josue answered me. So she says he in this moment have the connection problem.
Okay,
So maybe he can't to join with us in this moment.
So it's a good solution to make a recording, so you will be able later to return to the lecture and clarify some moments. Okay, so
yes, thank you, teacher.
Yeah, we will start. Discrete Fourier transform, direct and reverse. It means that we will consider the methods how to go from the initial original function that is normally defined at the time domain, like dependence on time, to the spectral area or to the area of images. And as a result of this, we will obtain the Fourier spectrum. Actually, it will be discrete Fourier spectrum, or shortly DFT spectrum. And using reverse method, reverse transform, we will be able to return back to the original function if we know the Fourier image, so we will be able to calculate original function. Okay, let's start. At first, because we are already going to the discrete methods, it means that we should talk a little bit about these differences between continuous and discrete signals. Actually, during this semester, we will deal mostly with the discrete method. So it will be mostly like not only signal processing, but digital signal processing. And also it's a very widespread and well-known acronym, DSP. You could meet it in some specialized literature, in data sheets, and also as regards to the special hardware, there are even specialized microschemes of processors. It's called DSP processors. So there is a specialized processors that are tuned for the digital signal processing. So they are adjusted to process signals using different methods, like we will consider, and also all other methods, many other methods. Okay, so if you are talking about digital system, then the signals that are going through the system are discrete. And sometimes the nature of many signals in the nature is analog. So in order to transfer and convert an analog signal to the discrete one, to the discrete form, it is necessary to make an operation that is called discretization. As a result of this operation, we will obtain the signal that is defined by its discrete values at some time interval. And the very important question is what should be the time interval when we take these discrete values. Because if you will consider analog signal, it could be different signal with a different nature, different origin. So when we are going from analog signal to the digital one, it is necessary to understand how often we should take the values of continuous signal in order to obtain relevant discrete signal. And it is a very important question. And the answer for this question, it is formulated like, could you see that I'm now selecting a phrase, a text, Nyquist frequency. This is a value that is useful to understand what is the necessary speed of discretization or what is the necessary frequency of discretization. And it depends of the value f max. F max is the maximum frequency and we can calculate this maximum frequency after the decomposition of analog signal into Fourier series, like you already know. You already know the procedure of Fourier series and Fourier transform. So we know, you know how to obtain instead an initial analog signal, the set of discrete harmonics. And each harmonics corresponds to separate frequency. As Robert today asked me about phi, so phi is like a phase shift, and the graph that you should construct in your first practical work is dependence of module and this phase shift from the frequency. And for different frequency, we will obtain different values of the module and phase shift of the signal. And these values, the values of Fourier spectrum at different frequency are called harmonics. And in general case, the number of these harmonics could be infinitely large. But actually, in practice, some of these harmonics, especially for the very high frequency, are neglectably low. So it's possible to don't take them into account because their amplitude is not so essential to make an essential influence to the behavior of the signal. That's why we can define some maximum frequency level. After that level, Fourier spectrum will contain only non-essential component. And this frequency, this threshold, will be called Nyquist frequency. You can see on the slide that F maximum is maximum frequency of the component with essential amplitude in original signal. So for different original signals, this maximum frequency will be different. Because sometimes for some signals, it could be only, let's say, couple harmonics, not more than 10. So we can define this frequency as maximum frequency as the frequency of the last non-zero harmonics. Sometimes if the signal is more close to the, like, let's say, white noise or something like this, so its frequency range could be quite wide. And it means that maximum frequency, sometimes it's very difficult to define. But anyway, it's a little bit another question that we are dealing now. So just for understanding what is it, because while we are going from continuous signal, from continuous functions to the discrete functions, it's very important to know what discretization frequency is eligible. So you can also search by yourself this term, Nyquist frequency. Nyquist is the last name of the scientist, and he investigated a lot frequency characteristic of different signals, and that's why this, this parameter is called after his name. Okay, so anyway, we assume that we have already discrete signal, and we are, it's for us at this stage already it becomes not so important how we obtain this discrete signal. So from a mathematical point of view, in terms of discrete Fourier transform, for us it's just important that that we already have a discrete signal that is to be analyzed. And this discrete signal means that we have just a sequence of discrete values. It could be situated, it could be formed like a vector, a horizontal row, or vector vertical column, or just a sequence written through comma and so on. And okay, here I don't see formula. Why? The question is why. I will try to open. I will try to open my Lection in PDF format, because today it was everything okay, but we will check. Here there are formulas, so everything okay. We can continue. If the font size is okay for you, Robert, Ahmed. The size of letters.
Yes, yes, okay. Yes.
Okay. So we have original signal that is defined by its discrete values with the equal time interval. And as a result, after Fourier transform application, we obtain, here is the original signal, here it is, where I'm just pointing it, it's x small from nt, so it's a time dependence. And this nt in a brackets, it indicates and it informs us that we are dealing with the time dependence. And this x from nt is an original signal that is assigned by its discrete values, x from 0, x from t is interval of discretization, x from 2t, and so on. And the last member is x from n minus 1t. So totally, in general, we have n capital. This is a number of discrete values of our original function. So our original function, we will indicate it like x small, and it is assigned by its n values. And as a result of discrete Fourier transform, applying to this original function, we will obtain the sequence of another n values, but the number of values will be the same, n. So how many digits we will have in original function, the same amount of digits we will have in the spectrum. And because it is a Fourier, we know that one of the main features of Fourier transform is that basic functions are complex value. So result Fourier spectrum will be also sequence of complex values. And we will indicate it like X capital. So capital letter always says us that there is a spectrum. And the small letter, it means that we are looking to the original function. And as regards to values of spectrum, so we have X capital from 0, X capital from omega. This is a capital letter omega that is like analogical to round frequency, x from 2 omega, and so on. The last member is x capital from n minus 1 multiplied by omega. So you can see that Fourier image is not depending on time. Time dependence, it's only original function. In the spectrum, we will have, in the best case, we will have frequency dependence, but it's only for Fourier method. For all other methods that we will consider during this semester, it will be like a mathematical abstraction. It will be not dependence on some physical value. It will be just like an abstraction. But sometimes its abstraction has a sense for application because it becomes more easy to calculate some parameters and investigate some features of signals using spectral methods. So that's why we will consider them also, not only stop at Fourier method. Robert is switched out. I think he has some problem with the connection, but anyway, we continue. So omega capital is the frequency of first harmonics, and it could be calculated like here, according to the expression below the slide, 2p over n minus 1 multiplied by t, where n is amount of discrete digits in original function and as well in the spectrum, and t is the interval of discretization. If this n amount of digits is quite large, it's in real application, it's really quite large. So it's extremely more than 1. So we can neglect this minus 1 and just approximately say that omega capital is approximately equal to 2p over nt, because 1 is neglectably less than n. Okay, and as I said already, and as you know, of course, Fourier transform, it's always complex value. And that's why as any complex number, it could be represented by real part and imaginary part. So each component of Fourier spectrum could be represented by its real and imaginary parts. And this representation is here in the first formula at our slide. And also using this and knowing these two components, we could be able to calculate the module of component of Fourier spectrum module x from k. It could be like a square root from the sum of squares of real part and imaginary part, like always. And also phase shift could be calculated like arctangents from the expression that is imaginary part divided over real part. It's very similar expression like a usual Fourier transform. Robert, are you with us now already? Hello, Robert? It's connecting. Okay. Do you hear me, Robert?
Yes, teacher. Sorry, I told you that I have a problem.
Yeah.
With the information,
Okay. Okay. So I continued now. And here in the slide, you can see formula number 1 that reflects the procedure of the calculation of direct discrete Fourier transform. So this is a formula that allows us to calculate the Fourier spectrum x from k. It's a discrete spectrum when we know original function x small from nt. So under the sum, we have original function, original sequence multiplied by exponent, and with this quite long expression in an exponent index, where we have I, j, k, omega, n, and t. But you can see that k is like a counter that could take the value from 0 till n minus 1. So for different k, for each concrete value of k, we could calculate the component of Fourier spectrum. And also it could be written in a symbolic form, like here that I'm pointing now. It's f with a lower index d. It means it's like a symbol of direct discrete Fourier transform. So when we are writing fd, it means that we should apply formula of direct Fourier transform here to some sequence some time dependence. And k is number of harmonic, like in usual Fourier transform as well. And here, this slide, it illustrates the connection between discrete Fourier transform and continuous Fourier transform. You should remember from the last presentation, when we considered continuous Fourier transform, we had a formula number 2 that gives us a value for the continuous Fourier spectrum, f from j omega. And if we will make some modifications and replacements in this formula, and these modifications are listed here at the slide, then we will obtain the formula for that will reflect the interconnection between discrete and continuous methods. These replacing are, firstly, instead continuous original function f from t, now we are placing x from nt. And even from this notation, you can understand that this is discrete function, unlike f from t. F from t is continuous function because we have a continuous time in a bracket, like a variable. And then instead round frequency omega, we will put k omega capital. And here it appears the counter k, like a number of harmonics and the number of spectrum component. Then instead continuous time, of course, we will put discrete time moments, that is n multiplied by t, and n is also, it takes a sense of counter because it could change and indicate the number of component of original function, the number of digits in original signal, and instead dt, in the integral we put t, like an integral, period of discretization, interval of discretization. And one more replacement, if in the formula for Fourier spectrum, because it was continuous, so we used integral, because for continuous function it could be applied, but for the discrete function it is impossible to make integration. So the analog of integral for discrete signals, it could be just a sum. That's why we put a sum here, and we obtain the spectrum of discrete Fourier transform. And we could mark and mention that the only thing that differs from it is the multiplier t. All properties are very common and similar for ft Fourier transform and dft discrete Fourier transform. And comparing 1 and 2, formula number 1 and formula number 2, we can obtain the very simple equation that reflects the interconnection between them. F from j omega is a continuous Fourier spectrum, and x from k is a discrete Fourier spectrum. So the only thing that connects them is multiplier t. T is the interval of discretization, the interval that we use in order to obtain discrete values from the continuous signal. So if we have continuous function, we just take its values from the equal periods of discretization. So the conclusion is components of Fourier transform are connected with digital Fourier transform components via interval of discretization t. This is like a very simple observation. And here for the illustration, very, very simple example, like always. So when we're executing very simple example and consider it in details, then we will be able to apply these tools for more complex signal. And of course, it would be possible because you will know absolutely clear how to do it, how to operate with this method. That's why we always consider starting with very simple example. And this simplicity here, it's that we take the original function, discrete sequence, that consists only of 4 values. Of course, it's very, very low because for practical use, for practical task of digital signal processing, it could be real signals that contains thousand and or at least hundreds values, but it would not be possible to reflect it on the presentation. So we reflect it and explain. I will try to explain you on the very easy examples, then you will do something similar at your practical work. And then I believe you will be able to do it in your own research, in your own work, if you will take if you will deal with some tasks that it will be necessary to use one of these methods that we considering now and will be considered during this semester. So we have initial sequence that is that consists only of 4 values, and these values are also very simple. It's 1, 0, 0, 1. In general case, it could be absolutely any kind of values, so they could be not only positive, it could be negative, it could be integer or simple or whatever. It could be like a result of experiment, for example, of some measurement of physical value and so on. But here in example, we have 1, 0, 0, 1, and our task is to find discrete Fourier transform spectrum for this simple sequence. And we should indicate firstly that our n capital, its amount of digital values, it's equal to 4. And we need to calculate, therefore, 4 complex values for the spectrum. It means that the counter of spectrum components k will be changed from 0 till n minus 1, but because our n equal to 4, so it will take the values k 0, 1, 2, and 3. Robert, you have some question?
Yes, teacher. I don't know if me again or what's happened, but I still see the last diapositive about discrete Fourier transform.
So now it's okay. Do you hear me? No?
Yes.
Ahmed, did you also have an interruption in listening me or not?
No, doctor. I think Robert mean we can't see the equation.
Equation? And now, do you see a slide here? Example 1 and so on.
No, I still see the slide that say signal sample. The last slide.
This one? No.
No, the slide number 3. I actually see the slide number 3.
Okay, so I just stop my sharing screen and then I will start again. And now, what you can see now?
Yes, now I can see the
connection with Fourier transform. Do you see?
Yes, now I can see this slide.
Okay, and now example 1.
Yes, exactly.
Okay, you should say me this a little bit earlier, but okay. Example number 1. 4 values of initial sequence 1, 0, 0, 1, and it means that amount of values n equal to 4, and the counter k, that is a counter of spectrum components, is takes a value 0, 1, 2, and 3, totally 4 numbers. And now we have to solve this just to find Fourier spectrum. From the expression number 1, here it is repeated also again, this expression. Do you see this? Expression number 1, x from k equal to, yeah, and so on. So we just apply this equation for different values of k, because k is our counter. So when k equal to 0, we will put this value into the formula, and we will obtain a first component of Fourier spectrum. Then we put k equal to 1, and we will obtain the next component. Then k equal to 2, and then k equal to 3. And then in such way, we will obtain 4 values of the discrete Fourier spectrum. So if k equal to 0, I think maybe later I would ask you to open this presentation from Google Classroom and attentively look to the example 1 and especially to the solution, because here it is explained very good. And after our lection, I will check again the files that in order to be sure that everything is reflected good. But you should understand it. It's not so difficult. It's just a very simple mathematical solution. And for example, for x equal to 0, we will obtain sum. And under the sum, we have x from nt multiplied by exponent in a power minus j multiplied by 0. Why multiplied by 0? Because k equal to 0 and k is present in a power of exponent. So any number in a 0 power is just 1. You should remember this. And as a result, our first component of spectrum will be just a sum of the component of original function. So we just have to add all the values from original function in order to obtain first component of the spectrum, 1 plus 0 plus 0 plus 1. So totally it's 2. And you see that it is not complex value, it's a real number. And actually for the first component of the spectrum for every function, arbitrary function, the first component of spectrum will be always not complex but real number, because always when we put k equal to 0, we will eliminate, we will drop the complex j, and we will have only the sum of the values of original function. And original function, that is time dependence or dependence of one physical value from the another one, could not be basically it could not be complex. It's always real because it's something that is that exists in real world, that could be measured, could be observed, could be visualized, and so on. So always x from 0, the first component of the spectrum, is a real value. And of course we can calculate the module of this value, and of course the module of the number 2 is just 2. And its phase also could be calculated, because the phase phi, Greek letter phi, is arctangents from imaginary part divided over the real part. And the imaginary part here is equal to 0. So arctangents from 0, it's also 0. So it means the phase shift for this first component of Fourier series is equal to 0. And then we just put in k equal to 1. And here we will obtain the value that is already not real. It's a complex value. I will not stop, if you don't mind, on this mathematical calculation. You can be later able to revise all of them and check yourself. The result will be 1 plus j, where j is a complex value. And here it's possible to calculate the module that will be equal to square root from 2, because real part is equal to 1 and imaginary part is also equal to 1. So the module will be square root from the squares, real part plus square of imaginary part. So square root from 2. And the phase also could be calculated. It will be arctangents of 1, because imaginary part is equal to the real part. And arctangents of 1, you should know this from geometry, from higher mathematics, from the previous courses. It's equal to 45 degrees, or in other words, p over 4. And also continuation of this example of the solution for k equal to 2. And here the result is a little bit surprising, because as you can see, the result is equal to 0. You can also observe and revise the consequence of calculation. But the issue is that result is equal to 0, and it means that it could be complex value with the real part equal to 0 and imaginary part also equal to 0. And the model is equal to 0, but how to calculate the phase? This is a question, because if we have arctangents from 0 over 0, so there is an uncertainty, and it is impossible to define the value of this phase shift. That's why the phase is uncertain here. But for the next one, when we put, so we just put it like here, uncertain phase, so uncertain, we cannot do nothing here. And for k equal to 3, we can calculate also the value of spectrum component, and it is equal to 1 minus j. It's a complex value, a real number, a real component and the real part equal to 1, and imaginary part equal to minus 1. But the model is still equal to a square root from 2, because under the square root, in order to calculate model, we should put real part in a square plus imaginary part in a square. So when we put minus 1 in a square, we will obtain 1. That's why model is equal to square root from 2. And the phase shift also could be calculated because it's arctangents of imaginary part over the real part. So minus 1 divided by 1, it means that arctangents of minus 1 is equal to minus 45 degrees or minus p over 4. And as a result of spectrum calculation, we will obtain the sequence that contains 4 components. First one is 2, second one is 1 plus j, third one is 0, and the last is 1 minus j. This is actually the spectrum of Fourier. And I would like now to stop considering this presentation, because I promised you to pay more attention to the practical work, yes?
Teacher,
Yeah.
before to continue, I have 2 questions specifically.
Okay.
First of all, where we can to get the value of upper n?
Of what? Value of
Upper
what?
n, n mayusk. We have n and n mayusk. Yes.
And this one, no?
No, that's another n, upper n. In the, for example, in the formula of the omega, we have the n mayus multiplied
N
for
capital, yeah?
n
This
capital,
one,
yes.
yes?
Yes. How we
Oh,
can?
it's very simple. You just should count how many digits you have in your original function, in your original signal.
Okay.
So here it's only 4. That's why n equal to 4. In real task, you could have a task when you should analyze the signal that could consist of hundreds values. So you should count all of them. You should know how many digits do you have in this signal. This is your n capital.
Okay, and another n?
Another small n, you mean, yes?
Yes, a small n.
Yeah,
Yes,
the
exactly.
small n is, just a minute, where it is. I will find here. So our original signal, yes? Here there is a digit, this n capital, you see? But the counting, we start counting from 0. That's why the last number is n minus 1. Understand, yes? So
yes.
if we have, for example, 4 values, so we start counting 0, 1, 2, and 3. So the last one is n minus 1. And this is a n small that is also like a counter. So we should put here n equal to 0, 1, 2, 3, and so on. It's also a counter.
Okay.
Understand?
Okay.
Yeah?
Yes,
So
yes, teacher, it must clarify.
For original function, we have a counter n for x small, yes? But for the spectrum, we have another counter, k.
Yes, counter k.
And
no, that is understanding.
Yeah, okay. So could I go to the practical? Yeah.
Yes, teacher, thank you.
Okay, where it is? It's not my courses. I should go back to our task. Number 1 that is already posted. Yes, here you can see. Did you see it already in a classroom? No?
Yes.
So I can open it again. And so your task is to calculate all of this like it was in the presentation. So you have the periodical sequence of the rectangular pulses with the same rectangular pulses that are identical, and there are parameters that are assigned according to your variant. You have your number of variant 1, 2, and 3, and you can put it here in the table, and you obtain the set of parameters of your own parameters for your own signal that you have to analyze. And your task is to find analytical expression for the Fourier transform dn. It means exponential form of dn. And also when you obtain this, then you will be able to find the expression for the module, because dn is a complex value. So you have to find the module and the phase. And then to draw the graph, like Robert asked, yes, how to do it. So there are totally 3 graphs. First graph is original signal. So you should build something like here. This is original signal. You should build it with your parameters, so it will be your own graph. Second one is a dependence of the module dn from the value n. And you should change in the range from -10 till +10. And it will be like a discrete values for the n -10, -9, -8, and so on till +10. And the same range of n you will use for the phi n. So you should find the value of phi n for each n. Okay, from -10 to +10. And how to do this? You can find again in classroom. Just a second here. In our presentation number 1. Let's have a look to it. Something with my internet connection now. I'm trying to open. Maybe here. No, I don't have it here.